sure they didn't come here.
Yeah. It's understandable, especially, I mean, at this point, it was 8:45 when this class was
Yeah.
almost over. So if I'm trying to combine those together, Katie, what do you do to combine two fractions together?
I multiplied the 3 times plus 2.
Because the goal is to also have an x plus 2 in the denominator. That 3, don't forget the little negative sign. Yes, it's minus 3, but that minus 3 also means negative 3. So that really says we have negative 3x minus 6. So Katie, if we combine the like terms on the top, what is our new expression in the numerator?
Negative 2x plus 6.
Yeah, negative 2x plus 6. So you could stop at this point and keep it as negative 2x plus 6 over x plus 2 because we combine them into one fraction. Or you could also factor the negative 2 out. And that would also be the same answer, just written a little differently with the negative 2 factored out. But that is simplified. By getting a common denominator, our goal is to combine the two pieces together. We're going to use that in about 15 minutes. Kind of just, we'll flip back to it. So what we're going to look at today are polynomial inequalities. And I don't want you to write anything yet because I want you to kind of get a visual as to what we're thinking about. So the most basic polynomial, an x with the smallest possible power, besides it being a line, would be an x squared. What kind of graph is an x squared graph? A parabola, so that's our u. Again, you don't have to draw this, so here's just a little parabola. We've been taking inequalities and like essentially some type of equation and showing where is it above the line or below the line, like the two I did with you at the beginning of class. So in this case, if I have a line, we'll say right here, because it's a polynomial or a parabola, I don't just have a piece that's above and below. I have two pieces that are above and one piece that happens to be below. But I could now have multiple parts of the graph above and multiple parts of the graph below. So it's not just this half is below and this half is above. Now I'm going to have multiple pieces. Our goal is to figure out how we can algebraically show where those multiple pieces of the parabola would be above or below a line. And when we look at the graph, graphs are above or below a given inequality. At its x-intercepts, which we know how to find x-intercepts. Factoring is one way, undoing is another way. Factoring works most times, but we know how to find x-intercepts, we know how to find x. That's what an x-intercept is, essentially solving for x. But these x-intercepts are called critical numbers. Critical number is an important piece of the graph. And the reason it's important is because those critical numbers are the locations of the graph that start to divide our graph up. So I would have a critical number on the left and the right that ends up creating spaces or intervals in my number line. So these critical numbers end up creating our intervals. So when you're asked to solve an inequality, it's not x equals 5. An inequality solution is an interval from negative infinity to 5 to 5 to infinity, from negative 3 to 10. So all inequalities have interval answers. And the way we find those intervals are going to be using by the x-intercepts from the equations. So that's going to help us then find intervals on the graph. So if you look at the first question, the word solve is very ambiguous. Ambiguous means a word with multiple meanings. Solving, usually your mind goes to find x. X equals 5, x equals 10, x equals 15. In this case though, if it's an inequality, solving an inequality means find the intervals. The hardest part of this is to train your brain to not just solve for x. We're still going to think about x, but those x's we're going to use to create intervals. So if you had a problem that said x squared minus 2x minus 3, what's the first thing that you would usually think about to do to kind of work through this problem? Maya.
Factor.
And we're still going to factor. So Maya, if you factor this, you end up with -3 and 1. I'm going to omit the inequality symbol right now and just work with the factoring. So typically I would say x equals 3 and x equals -1. But instead, I'm still going to use those they are going to become our critical numbers. Oh, there we go. Okay. Sorry. So our critical numbers are 3 and -1. So in theory, you're solving, but I'm not saying x is equal to this because it isn't equal. It doesn't have an equation symbol. So once you find your critical numbers, we're going to put those numbers on our number line. Because then that gives me intervals. So my solution will either be everything to the left of -1, everything in between -1 and 3, or everything to the right of 3. And that's because if I have a graph, I like break something. If I have a parabola, and that's below, and another section that would be above the value of 0. There we go. So here's my little parabola picture. So those numbers that we have could represent this and could represent this here so that I have pieces above and below. The way I determine if that piece is truly above or below is to do a little test. So we're not actually doing a lot of algebra, we're doing a proof. Ooh. Yeah. So we are going to test to see which one of these hold true with our given inequality. And this is now where this symbol comes in. So we're going to pick 3 numbers that fit within this kind of specified intervals that we have. So a number less than -1 could be -2. You can pick anything, but make it small. We're trying to pick a number that would be in this interval that we could test to see if it works. Is it greater than 0 when we plug it in? An easy number between -3 or -1 and 3 is +1 or just 0. 0 is really easy. And then a number bigger than 3 is 4. When you plug them into the original inequality, if it remains true, the left side is bigger than the right, then that interval is your solution. If it's false, then that interval is not your solution. So plug it into the original equation. Take in the -2. I need to prove that that's greater than 0. So the inequality is actually part of like the last thing that you're using. So you're breaking the number line up into these values, and then we're using the inequality last by kind of testing a couple of numbers. So -2 squared is 4. This is supposed to be a negative. In here, -2 times -2 is another 4, so 8 minus 3 is 5. and 5 is greater than 0. That's true. So I'm going to just give myself a little shading so that I know I tested it, it's true, it's part of the answer. The middle is a 0, so 0 squared, 2 times 0 minus 3. Negative 3 is greater than 0? No way. Cross it off, not your solution. The last one is plugging in a 4. 16 minus 8 minus 3 is also 5, and 5 is also greater than 0. So we've proven why this graph works, why the graph has 2 pieces above, which is greater than, and that inner, like that center piece, which is less than or below. So how would you write your answer? Solve means to find intervals. So how would I write those intervals? What are the intervals for the graph that are greater than 0? Odette? So negative infinity to negative 1, because at negative 1, it stops being above 0. And negative 1 gets a bracket or a parenthesis? Parenthesis, because it's just greater than. And then the other interval, Odette, would be? 3 to infinity. And again, we got parentheses there. Questions? So we're going to go through the next one a little quicker, but I'm going to change that 8 to a 9 just to make it a nicer radical so we can take the square root of it. But your answer will look like interval notation. You're not really solving for x. Questions? So the one underneath, I'm going to change that 8 and make it a 9. Again, it says to solve, which really means find the intervals, not x. I'm not finding x equals 5. I'm finding the intervals that satisfy the conditions here, which is less than or equal to 9. So how would you traditionally solve this problem? Connor, what do you think? How would you traditionally solve something where you have quantity squared?
Take the square root of both sides.
Take the square root of both sides. We're still going to do that. So you still do some stuff that's the same as an equation. And Connor, you end up getting
X plus 6 is less than or equal to 3.
or
Plus minus 3.
plus or minus, yeah. Okay, that's where the solving stuff stops. So now I'm going to list my critical numbers. Again, I'm not going to say x is equal to 3, but we're going to get those critical numbers. So Connor, if you subtracted the 6 to the other side, those two values that you would have.
Negative 3 and negative 9.
Perfect. Place those numbers on your number line. Negative 9 is smaller. And now I have 3 intervals where the graph could be above or below my 9. So pick numbers to test. I do need to see a proof as to why you're choosing this piece to be above, this piece to be below. So pick easy numbers like negative 10, maybe a negative 4, and a 0. So pick 3 numbers, prove that that part is definitely above or below the 9. And we're looking for it to be less than or equal to the 9. So if I plug in a 10, a negative 10, I need to make sure that's less than or equal to the original problem of 9, and that is 16. 16 is not less than or equal to 9. If I plug in a negative 4 plus 2, or negative 4 plus 6 is 2. 2 squared is 4. 4 is less than or equal to 9. And then I always choose 0. If I could pick 0, I want to pick 0. 0 plus 6 gives me 36, which we know is definitely not less than or equal to 9. So I need to see the numbers you're choosing, and I at least need to see this here. You don't want to show that other scratch work, that's fine. That would be like a little verification that the numbers are working. So what's your solution? Find the interval. What's the interval of the graph that's less than or equal to 9? Yeah. -9 to -3. And is it brackets or parentheses? Brackets, because it's less than or equal to. Questions? So we're still doing some things similarly, but they're not really called the same thing. So I'm not solving truly for x. We're using those numbers to help us get these intervals. So we're going to skip the problem at the top. Essentially, this is asking you to plug this in your calculator, plug in the 1, and see where the shading is above or below. Like the 2 warm-up problems, except this is a parabola instead of a line. If you go to the next problem underneath, this is the problem that I told you to kind of remember. We're going to flip back to in a couple of minutes. So if you can flip back to that page and simplify this. Remember, we're not solving. So I know every piece of you wants to find x. You want to take the 3 to the other side. You want to get rid of that x minus 2. But we're not finding x. We're trying to find the interval. And to find the interval, we need to use the x-intercepts, but we also need to use the place where it's undefined. So any x-intercept or any location that's undefined, create those critical numbers. So it's pretty much the same as the 2 problems we did, except now there's a denominator. And the denominator is a place where it breaks up the graph. So anything that makes the denominator 0 doesn't exist in the graph. Therefore, it's going to kind of be used in one of the numbers or one of those sections in our graph for it to be broken up. So can anybody remember what the equation was or the expression was that we got on the other side when we simplified it? What was that expression when we simplified it? Abby, what do you have?
-2 times x minus 3 over x plus 2.
So that was our expression. Again, instead of solving, we're going to combine those 2 fractions together. We're going to simplify it. And then greater than equal to 0. So last year was a while ago. Chapter 8 was also a while ago. And when we did these problems in Chapter 8, we found x-intercepts, we found asymptotes, we found y-intercepts, we found, what else? X, y-intercepts, horizontal, vertical asymptotes. That's the information we found. But each piece of the fraction found a different piece of the graph. The bottom part is what makes the fraction undefined. How would I figure out the number that makes it undefined? What does that mean if it's undefined? Mackenzie? You weren't raising your hand. No. Jacob?
Equals 0.
It equals 0. So Jacob, what number would make this equal to 0?
-2.
-2. So this can't be -2 because it's undefined, so one of my critical numbers is -2 because x cannot be -2. It makes it undefined. Remember, that creates that space in the graph that doesn't exist. That's going to create an interval then on our number line. So the undefined value is always from the bottom of the fraction. The x-intercept is found from the top of the fraction. So the top of the fraction gets us the x-intercept. So fractions are kind of nice. The top finds you an x-intercept, the bottom finds you the undefined value. And that's found again by taking this and setting it equal to 0 and finding x. So if you divide by -2, take the 3 to the other side, my x-intercept is 3. So the x-intercept is 3. The undefined value is negative 2. So numerator, x-intercept. Denominator is where it's undefined. And then when you have those two values, you're going to create your number line. Sometimes you're going to have 3 values. Like one of the homework problems, you're going to end up having 3 values. So then you place all 3 numbers on the number line. So now we're testing them. I'd suggest testing it into the expression here, or if I distribute, this is negative 2x minus plus 6 over x plus 2. I'd suggest using that one. Because you're going to be plugging numbers in. You want to make it easy on yourself. Easy numbers to plug in. So negative 3, pick a good 0, and 4. So our goal is to find the locations that are greater than or equal to 0 of this rational function. So again, I plugged it into the simplified version without it being a factor. So the last step is to look at your inequality. Which one of these are greater than or equal to 0? So the inequality is like the last thing that you're kind of comparing. The first one, I have negative 12. Negative 12 is not greater than or equal to 0. Put a little x there. 3 is greater than or equal to 0, so if it works, I shade that little section in. Negative 1/3 is not greater than or equal to 0, so that is not a solution. So you're using the numbers to test to see which interval works with the condition being greater than or equal to 0. And then the last part would be actually to write the solution. So I know it's in between these two numbers. We just need to write it as an interval. Odette, what do you think?
Negative 2.
So I agree with a bracket around the 3, but a parenthesis around the 2 because of this little piece here that x can't be 2, because then it makes the denominator 0. That's the tricky part. So bracket with 3 because it does say greater than or equal to. It's allowed to be 3, that's an x-intercept. It's not allowed to be 2 because that's what makes the denominator 0. So we have about 5 minutes. I'd like for you to kind of look at your homework, and I want you to look at one of the problems so we can just kind of start it together. This might be a little more thought-provoking than the other homework assignments. We're going to look at number 3 so that we can do another one of these and really start it together. This is on page 14. Solve the inequality, graph the solution on a number line. Write your solution in interval notation. You can use a graphing calculator to verify. So on this left side, we have 1 over x minus x, and it's greater than 0. How would you start the problem, Jacob?
X cannot be 0.
Okay, so we know x, what else? Okay, so before, yes, you're right, but before we get to that, what should we do with those two fractions?
Find the least common denominator.
Find the least common denominator. So, Jacob, what would the least common denominator be?
X.
X. So now I have x times x, which is x squared. Okay. So we combine them together to have one fraction. That's the first step. Combine them, simplify. We need to get our critical numbers. And they are found by the undefined value, and Jacob already said x cannot equal 0. And that's because you can't have 0 in the denominator. So that's one number that's going to go on the number line. The other one would be those x-intercepts. How do you find an x-intercept? Kevin? Solve for x on the numerator, the top part. So we're going to solve for x on the top part. So 1 minus x squared. So Kevin, if I solve for x here, we get negative x squared is negative 1. So what would the x values be? Right. So x is 0 or can't be 0 is a critical number. And the plus or minus 1 is also a critical number. So the x-intercepts, finding the x of the numerator. The undefined value is the x in the denominator. Make yourself a number line. It says to graph the solution of the number line, so we already got that part going. And then I'm going to put those three values. So we have a number at negative 1, we have a number at 0, we have a number at positive 1. And now you need to do the test intervals. So negative 2 is less than 1, positive 2 is greater than 1. What number could you pick between negative 1 and 0? Negative a half? Got a fraction to work with. Or you can use negative 0.5. And then we might as well use positive 1/2 or positive 0.5. So you probably want to use a calculator to help. But you're taking this inequality and we're trying to see if it's greater than 0 by plugging in these test values. So now I have 4 to check. So again, you can plug them into your calculator. I just need to see the number that you're comparing to 0. So this would be, what, negative 3 over negative 2, which is greater than 0. So I would shade this part of the graph. So 1 minus 4 is negative 3, the denominator is negative 2, 3/2 is bigger than 0. So that part is part of the solution. And then test the next one, test the third one, test the fourth one. Questions? Please use your notes as a reference. Have an awesome night.